Swayam Prabha. Digital India. Educated India.
Hello everyone. Now our present topic is roving frame. We will start this section with basic understanding of roving frame. This we have already done in yarn manufacturing courses, but here what we will try to understand the twist, how the twist is being incorporated, and what is the relationship between bobbin motion, bobbin RPM and related numericals. Few numerical we will try to solve to understand the motion relationship between different motions, and later we will try to go further mechanisms in roving frame. So, winding on a bobbin is very complex, which actually bobbin gets drive from the epicyclic gear. Here again that we will discuss subsequently. So, here if you see, the twisting is not that critical here, because twisting is done by the flare which rotates at constant speed, but winding is a complex system. The roving bobbin carries a relatively large quantity of material due to its compactness, large quantity. The taper angle is important. We have to have certain taper angle. Actually, that is basically to increase the stability of the package. So, larger angle, more material will be there, but the stability will be less, and for that we have smaller angle. So, bobbin drive are basically, there are two types of drives, one is called flare leading, another is bobbin leading. So, flare rotation, actually it is a constant rotation, that we always keep the flare rotation constant, and the winding takes place due to the relative motion of the flare. So, we normally change the bobbin rotation. So, this difference in peripheral rotation of bobbin and flare is also kept constant, and here is actually comes the complexity, because we have to keep this peripheral speed difference constant just to maintain the delivery speed, but at the same time the problem comes that bobbin diameter changes. Bobbin diameter gradually increases with every layer of winding, and that is why we have to change the speed of the bobbin accordingly after every layer. So, bobbin RPM is continuously reduced in case of bobbin leading, as this picture shows. It is a bobbin leading mechanism. We can have flare leading also, where flare moves at rotates at higher speed than bobbin, but here in bobbin leading, bobbin rotates at higher speed than the flare. So, bobbin's RPM has to be reduced continuously with the increase in diameter. So, here, and this is achieved using the cone drum mechanism. This cone drum mechanism we will discuss separately, and with the differential gear. So, cone drum mechanism, differential gear and their relationship we will discuss separately, and this cone drum mechanism, that the differential motion, the changing motion is achieved by the shifting of cone belt. That shifting mechanism also we will discuss. Okay. So, U1 and U2, the relationship between U1 and U2, U1 is the RPM of the top cone drum, and top cone drum RPM is generally it is a fixed, it is a fixed RPM. Okay. And bottom cone drum, it is U2, which is variable and it varies due to the shifting of the cone belt. So, initially it is a, if it is say higher speed. So, that means initially the bottom top cone drum diameter will be maximum and bottom cone drum diameter will be minimum. So, that means it will transmit maximum speed, and gradually if the belt is shifted in this direction towards this, that means it is shifting towards the lower diameter of the top cone drum and higher diameter of the bottom cone drum, and accordingly the speed reduces. So, moving the belt in direction x, okay, that is in the direction x. So, it will increase the speed of the U2. So, if it is in x direction, and if it moves in the y direction, in this direction, that means the speed will decrease. So, and this variable motion from U2, it comes to the differential gear, and one constant motion comes from the main shaft, that is top cone drum, related to top cone drum speed, and these two motions are superimposed, and ultimately it gives RPM, certain RPM, which is coming to the bobbin. So, this total detail arrangement, detail mechanism we will discuss separately. One is cone drum mechanism, shifting mechanism, and the differential gear mechanism. These things will be dealt separately, but at present we are trying to understand the basic twisting mechanism and their relationship. So, cone drive transmission is that cone profile is there, the variation in bobbin rotation rate occurs in small steps owing to the shifting of the cone belt. After each stroke, each lift. So, that means after each lift there will be increase in diameter, okay, and as the diameter increases, the bobbin speed has to be changed, and that is changed by shifting of cone belt. The bobbin winding speed reduces in a hyperbolic fashion as the bobbin builds up, because we are talking about the bobbin leading mechanism, but in fly leading mechanism the bobbin speed has to be increased. So, winding speed equal to winding RPM equal to delivery rate by pi dt. dt is the diameter of the bobbin at time t. So, bobbin diameter, and which is k delivery speed by pi d, d0 is the initial diameter, and 2 N1T number of wrap, and dr is the diameter of the roving. So, for each layer the diameter of roving will change by 2 times of the diameter. Okay. So, empty bobbin diameter d0 and dr is the roving diameter. So, k by pi d0 2 pi dr nt, and this is k by a plus a is a constant, this is a constant, and 2 pi dr is constant if is the bobbin the roving diameter if we assume as a constant, and nt is the number of layer. So, it is bobbin winding on speed is changing with the number of layer. What is winding on speed? Winding on speed is nothing but the relative speed between the bobbin and the flare. So, winding speed if the bobbin diameter it reduces. So, bobbin lead and flare lead, the difference is that in bobbin lead, as the diagram shows, bobbin surface speed is faster than the flare. Bobbin winds the roving on itself. So, that means when the bobbin rotates the on its own its winding, that means if there is any breakage and that end broken end will be lying on the surface. The advantage in case of roving brakes, the direction of roving on the bobbin provides a stable outer layer. So, it will not get disturbed, and the drive to the spindle is shortest. So, bobbin gets drive through long distance, that we will discuss. It goes through the cone drum, then differential gear and differential gear output, then coming to the bobbin. So, it gets a longer path, whereas the spindle or flare the drive is from directly from the main shaft. So, flare is actually gets motion through the, as these are getting motion through the mechanical system, there will be some time lag. So, flare gets in motion at the faster speed, little bit earlier than the bobbin. So, this leads to more roving brake. If the flare leading is there, that means there will be sudden jerk, because flare will start motion at as flare is moving at faster speed, and as well as it has got early detection. So, immediately it will there will be breakage. Okay. We can see here the flare, the spindle, this is spindle directly from the main shaft, it gets directly motion in the shortest route. But whereas the bobbin gets motion from this differential gear, and differential gets motion, this gets motion through this arrangement, top cone drum, bottom cone drum, and all this arrangement. So, it gets motion this from the differential gear, and then it is going to the bobbin. So, longer distance, longer path is followed. So, bobbin, and another advantage here is that bobbin speed reduces in bobbin leading as the diameter increases. So, that means your total energy consumption, energy required will be almost balanced. Okay. Otherwise, in case of flare leading, as it is flare, that bobbin gets bigger and bigger and its speed also increases. So, we can see the flare speed, flare leading, flare speed is faster, and flare winds the roving on the bobbin surface. Okay. That is, this is flare leading, here is the bobbin leading. Now, twist in the roving. So, twist should be as low as possible. Ideally, given an opportunity, if we can handle the roving, it should be 0. Because we cannot handle, we need a minimum strain, that is why the minimum twist is required. Okay. Because here the twist has to be broken, removed in the ring frame, and there is no untwisting mechanism in a ring frame, only the twist is removed by the small stretch which is given at the brake draft zone, back zone. So, that twist has to be removed. So, that is why it should be as low as possible and roving diameter is proportional to the text, and we can see as the roving diameter increases, okay, that means you have to, you can see here roving diameter, and this is related with the twist angle. Twist angle is given beta. So, you can see sin tan beta equal to pi d by h. Pi d is the diameter of the roving, and h is per the 1 by t, t is the turns per unit length. Okay. So, h is for one twist what is the length. So, pi dt we can see here, and for the same twist angle, okay, length twist per unit length is actually proportional to the roving diameter for twist, same twist angle. So, twist angle if we keep, that means is inversely proportional to the roving diameter. So, tan twist angle beta controls the draft characteristics. That means, if we are producing coarser variety, coarser, so we have to keep the twist angle same, twist angle same. So, we have to keep the twist per unit length less twist length, because this beta actually controls the drafting characteristics. If we increase the beta, or if we this twist angle is increased, that means there will be a drafting problem will be there. And in bobbin leading, the winding is affected only when the difference between bobbin and flare assembly is equal to the delivery speed. Okay. That's otherwise the, if there is any imbalance, there will be immediately breakage. So, there cannot be imbalance. If it is the feeding is more, then there will be a breakage, and if it is feeding is less, delivery is less, that also will cause breakage. So, this equation, the d is the delivery rate, pi dt, dt is the bobbin diameter at any instant t, equal to Nb minus Nf, which is in case of bobbin leading mechanism. This equation has to be maintained perfectly, because the bobbin, the roving which we are producing, it is a very weak. Okay. Otherwise, if we do not make this, maintain this equation, there will be immediately breakage. Okay. Here the thing is that d is constant, Nf is constant, flare speed is constant, that is flare is fitted on the spindle. So, flare Nf is constant. So, diameter of bobbin increases continuously after every layer. So, that means to maintain this equation, we have to reduce the bobbin diameter, bobbin RPM. So, that is important. Bobbin RPM has to be reduced after every layer of roving production. Okay. So, d is the delivery speed, dt is the bobbin diameter at time t. Now, as dt increases, Nb has to be reduced. So, with the time, bobbin speed has to be reduced, okay, for bobbin leading, and for flare leading it has to be increased. Owing to increase in bobbin diameter, and also to maintain the increased wound length per coil, the bobbin rail speed has to be reduced. So, bobbin, not only the bobbin RPM, bobbin rail speed has to be reduced, because this the as the diameter increases, we have to place the next coil exactly adjacent to that. For that, as the diameter increases, one coil will take longer time because delivery is constant. So, one coil will take longer time. For that we have to reduce the speed, okay, of the bobbin rail, and in flare leading winding is affected only when the difference between bobbin and flare assembly is equal to the delivery speed, that is same Nf minus Nb, the delivery speed d, and dt is the bobbin diameter at time t, and as dt increases, as dt is constant, this d is, as dt increases, to maintain this equation Nb has to be increased. Going to increase in bobbin diameter, also to maintain the increased wound per coil, the bobbin rail speed here must be reduced. So, the thing is that here in flare leading bobbin speed has to be increased, but bobbin reel speed has to be reduced. Okay. So, the main requirements of modern roving frame, this is the schematic diagram here. Simpler machine, less liable to fault, spindle speed has to be increased, package size should be more, these are the requirements. Machine automations must be there, automatic transportation should be there. That means, here the flare has to be removed, flare will be top mounted flare is required, not the cylinder mounted. So, this is the top mounted flare, not the spindle mounted. Earlier it was the spindle mounted flare, but in case of modern automated doffing we need top mounted flare. Now, flare imparts twist, and that is the turns per meter is the flare RPM by delivery speed in millimeter per minute, that is the flare RPM is constant. Now, we can see here for different types of roving. So, if we increase the roving linear density, so roving linear density in terms of any, it is roving becomes finer. So, if we make the roving finer, so twist has to be increased, okay. And for longer fiber we can use lower twist for same, and for cotton we keep little bit higher twist than the polyester, because polyester fiber length is longer. And so, you can see that even for polyester, short polyester fiber and long poly 60 millimeter, 40 millimeter, there when we are using the longer fiber we use lower twist, okay. And even with the same fiber length, when we use finer roving, the finer fiber 1.2 denier and 2 denier. So, 1.2 denier fiber will need lower twist. So, depending on the fiber, denier, fiber length, okay, and also roving linear density, we can adjust the twist, required twist. So, here this we have already discussed. So, high twist is basically loss of production. So, flare speed is constant. So, for we do not need high twist, and that will that's production loss is one issue. The main problem is that drafting problem. It will create drafting problem in ring frame, and low twist false drafting will be there. So, we cannot keep the twist very low level, because otherwise in the ring frame, during ring frame there will be some false draft. Roving breaks during bobbin winding. So, during that it will break. So, we have to maintain the optimum twist. So, tan theta is a pi dt, okay, theta is proportional to t and in also proportional to d. As a d increases, theta also increases. So, d is the roving diameter and tan theta we can calculate. The twist per unit length is equal to tan theta by pi d, and tan theta the d is a 1 by k under root n. So, that we can calculate. So, this k and this one, this is a constant for a particular theta. If we keep theta constant, so that this will be constant. This is known as the twist multiplier, and the Tm is actually is nothing but it actually shows the angle of twist angle. So, as the twist angle increases, Tm increases. So, higher Tm, higher twist angle means its draftability will be poor. So, we cannot keep the higher twist multiplier in roving. This is twist multiplier which is constant for a certain theta. That means, twist multiplier actually indicates the twist angle. Now, in older flat tops, smooth metal, and newer flat which are grooved or notched rubber inserts. This is a rubber grooved or notched which inserts the false twist, and false twist basically is advantageous because it is reduces the fly generation. False twist means it will have the higher twist in the unsupported zone, that is between the front roller nip to the flat top. So, the front roller nip to the flat top, there in that zone you will have higher twist, but ultimately in roving the twist will be cancelled out, it will be normal twist. Inserts false twists, that is a newer flat top which reduces the roving breakage in spinning triangle because of the higher twist level, reduces the fly and lap formation, more compact roving is generated and high bobbin capacity. So, as the compact roving we are getting, so high bobbin capacity, but the effective twist is same. That means, it will not have the drafting problem and reduce false draft due to the wrapping of fiber, not the twist, effective twist. A roving fineness difference from front and back row is minimized because of this. And now we will discuss a few numericals related to roving. Now, see a bobbin leading speed frame, that is roving frame running at 1000 rpm spindle speed is producing a roving with 2.5 turns per inch. The diameter of empty bobbin is 5 centimeter. When the bobbin attains 10 centimeter diameter, the percentage change in bobbin speed will be. That means, initially it is bobbin leading, initial the empty bobbin diameter is 5 centimeter, and we want to calculate the change in speed. That means, speed is reduced when it has attained 10 centimeter diameter. We want to calculate the percentage reduction in bobbin speed. So, this is the bobbin leading. So, suppose at the initial when the bobbin diameter was 5 centimeter and at certain speed at this point here, this is the bobbin and here we have reached the speed when it is a 10 centimeter diameter. So, we want to calculate the what is the percentage reduction, These are the given data, twist per inch is given 2.5. So, we can see these are the spindle speed is 1000 rpm, twist per inch is 2.5, bobbin diameters are 5 centimeter and 10 centimeter, and percentage change in bobbin speed we have to calculate. So, turns per meter is flare speed or spindle speed the same by delivery speed, that is the turns per meter. So, delivery speed will be in meter will be spindle speed by TPM, that is the delivery speed, and this is in inch, okay. And if we want to convert into meter by 39.37. So, spindle speed or flare speed is given and TPI is given. So, delivery speed will be 1000 by 2.5 and divided by 39.37, it will be 10.16 meter per minute. That is the delivery speed from the front roller, and that delivery speed has to be, we are actually considering there is no contraction, twist contraction, and their delivery speed has to be actually wound by the winding system. Now, try to see bobbin speed at 5 centimeter bobbin diameter is Vd, which is calculated pi dB, Ns is known, Nb we have to calculate, dB is given 5 centimeter. Now, try to see here. So, 10.16 meter per minute we have calculated, and pi and 5 centimeter means 0.05 meter, and Nb we have to calculate, and flare speed or spindle speed is given 1000. So, from this equation we can calculate the bobbin speed at 5 centimeter diameter, and it is coming out to be 1065 rpm. Okay. Now, for 10 centimeter diameter, delivery speed will remain same, okay. Delivery speed will remain same and Ns will be there, delivery speed is same, only thing we have to calculate the Nb for 10 centimeter diameter, that is. So, delivery speed is Nb for 10 centimeter diameter, it is becoming 1032.35 rpm. So, that we know the speed, initial speed, bobbin speed, and the speed at 10 centimeter diameter. Now, we can calculate the percentage change in bobbin speed, okay, between 5 centimeter diameter and 10 centimeter diameter, and what we will be getting is this is approximately 3%. So, this is initial, and at 10 centimeter it is reduced and divided by 1065, it is 3%. Okay. Now, we have several other numerical, and we will stop here, we will continue with this numerical in the next session. Till then, thank you. you.